Welcome to this explainer. Okay, let's dive into this. Today we're taking a pretty fascinating journey into the literal building blocks of the materials all around us. We're going to demystify some metallurgy basics and tackle a question that seems super simple on the surface, but it's actually rooted in this incredible, invisible world of atomic physics. That question? Why do things rust?
You know, when we normally think about rust, we just picture aging metal, right? Like an old car, a weathering bridge, or maybe a forgotten wrench left out in the rain. But what if I told you that corrosion is actually an invisible quantum battle happening right in front of our eyes? To really grasp what's happening to that piece of iron, we can't just look at the surface. We have to zoom all the way in and look at the atomic structure. So here's our visual roadmap for today. First, atomic structure and electrons. Second, metals versus nonmetals. Third, electricity and electron flow. And finally, the true definition of corrosion. We're building this up from tiny atoms all the way to why massive bridges rust.
All right, kicking things off with Section 1, Atomic Structure and Electrons.
So, when we zoom into the atom, the real stars of the show are absolutely the electrons. They sit in these organized paths called shells, and the way they arrange themselves follows a super simple mathematical rule, 2n squared. Basically, shell 1 holds 2 electrons, shell 2 holds 8, shell 3 holds 18, and so on. This precise filling order, that's exactly what gives every single element in the universe its unique identity.
Moving right along to Section 2, metals versus nonmetals. And what's really interesting here is how those electron shells determine a material's very identity.
It really all comes down to that outermost shell and the electrons living there, what we call valence electrons. Let's compare two totally different elemental characters. Over on the left, we've got sodium, atomic number 11. If we fill its shells using that rule we just talked about, 2 in the first, 8 in the second, that leaves exactly one lonely electron just hanging out in the third shell. Now, on the right, look at chlorine, atomic number 17. That's 2 in the first, 8 in the second, and 7 sitting in its outer shell. This difference? It's literally everything. Sodium has this single outer electron it's super eager to lose, which makes it a metal. Chlorine, on the other hand, is holding on to 7 outer electrons and is incredibly stubborn. It is not letting them go. That makes it a nonmetal.
So, by just counting those outermost valence electrons, we can basically categorize every material out there. If an atom has 1 to 3 valence electrons, it's a metal, which, by the way, also makes it a conductor. If it has exactly 4, it sits right in the sweet spot as a semimetal or semiconductor. But if it has 5 or more valence electrons, like our buddy chlorine, it's a nonmetal, and it acts as an insulator. It all comes down to just counting from 1 to 8.
Okay, let's jump into Section 3, electricity and electron flow. Let's see how all this builds up.
Now, we really need to clarify a crucial distinction here. When you hook up a battery, traditional electric current is said to flow from the positive terminal to the negative one. But physically, at the actual atomic level, the electrons themselves are moving in the exact opposite direction. Since electrons have a negative charge, they actually travel from the negative pole toward the positive pole. You've got to keep this actual physical movement in mind because the ability of those electrons to move is exactly what defines a conductor. And this distinction brilliantly illustrates why metals conduct electricity while insulators just don't. It's all about how tightly the nucleus is gripping those outer electrons. Conductors, the ones with just 1 to 3 valence electrons, have what we call free electrons. The nucleus doesn't really have a strong grip on them, so they easily detach and just flow right through the material. But insulators, the ones with 5 or more outer electrons, they have bound electrons. When an atom has that many electrons in its outer shell, the attractive pull from the nucleus becomes overwhelmingly strong. I mean, they're locked in. The electrons cannot escape. And hey, no free electrons means no flow of electricity. It's actually that simple.
Which finally brings us to Section 4, the true definition of corrosion. Let's solve our initial mystery.
I want you to think about this for a second. You can leave a piece of plastic or, say, a chunk of glass outside for literally decades, and it won't rust, right? But leave a piece of iron out, and it deteriorates so fast. So why do metals rust but insulators remain completely untouched by this specific process? Well, get ready, because we're about to totally rethink everything you know about rusting. Here is the absolute core definition. Corrosion is the loss or emission of electrons. It's not just a piece of metal getting old or dirt piling up on it. At the foundational atomic level, corrosion is strictly the act of an atom having its electrons stripped away. Bottom line, if electrons are leaving the material, it is corroding. Okay, let's walk through this logic step by step. We know metals have 1 to 3 valence electrons, right? And as we just saw, they lose those electrons super easily. Well, because they easily lose electrons, they easily corrode. In fact, a metal with just 1 loose outer electron is highly vulnerable and is going to corrode way faster than a metal with 3. On the flip side, look at insulators. They have 5 or more valence electrons, and that nucleus is holding them incredibly tightly. Because these materials physically cannot be forced to lose their electrons, they absolutely cannot corrode. Insulators are literally immune to rust because their atomic grip is just way too strong.
Which brings us to a really fantastic final thought. If corrosion is fundamentally just the loss of electrons, can we prevent a metal from rusting simply by supplying it with a constant stream of new electrons? Well, the answer is yes, and it's an actual real-world engineering trick they use to protect massive ships and pipelines. By understanding the atomic secret of rust, we don't just understand why things decay, we literally learn exactly how to stop it. Thanks for joining me on this explainer, and definitely keep questioning the science hidden just beneath the surface.